session of the soil mechanics. This will be based on the consolidation settlement. So in this Q&A, I have totally 4 questions. The questions will be uploaded to my website and I will leave a link to that. The first question is, a specimen from a natural saturated normally consolidated clay stratum has a natural moisture content of 65%. So it states that the water content is 65%. The specific gravity is 2.72 and the vertical effective overburden stress is found to be 150 kilopascal. So that is the vertical overburden stress. So that is the sigma V naught dash, which is the effective stress, which is 150 kilopascal. The pre-consolidation pressure is given as sigma P is given as 210 kilopascal, and the respective CC and the compression index CC, it is 0.4 and the CR is 0.02. So these are the data given. Determine the resulting void ratio due to the load increment of 50 kilopascal. The first question is, they have given that the first part is the load increment, that is the sigma delta dash is 50 kilopascal, and they want us to find the resulting void ratio. So that is the EF. So here first we have to consider whether the soil is in an over-consolidated state or normally consolidated state. So even in the question they have stated as normally consolidated. You can even check that the initial load is 150 kilopascal and the load increment is 50 kilopascal. Load increment is 50 kilopascal. So the final load, so this is the sigma 2 dash, would be equal to 150 plus 50, so that is 200 kilopascal, which is less than this pre-consolidation pressure. So still the clay hasn't gone into the normally consolidated state, so it is still in the over-consolidated state because the maximum pressure is 210, so it is experiencing a pressure which is less than its pre-consolidation pressure. So we have to use the CR index. So from the graph we know the gradient CR can be written as change in void ratio over log sigma 2 dash over sigma V naught dash. So these two are the pressures which we know exactly, but we don't know what is the initial void ratio. To calculate the initial void ratio, we can use these two parameters, that is the W and GS. We know E is equal to WGS over S. Since this is a saturated clay, S is equal to 1, so W is equal to 0.65 into GS 2.72 over 1. So this would give us an answer of 1.768. 1.768. So this would be the initial void ratio E naught. So since we know what is E naught, we can simply substitute those into the equation 1. So from equation 1 we can get as 0.02 is equal to change in void ratio, this is 1.768 minus EF, the final ratio. Since the soil is getting over consolidated, the void ratio will be reducing, so this would be lesser over log 200 over 150. So by solving this, we can find what would be the final void ratio. So I'll erase here. The final void ratio EF from 1, the final void ratio EF can be calculated. It is 1.766. So that is the first part. It's very simple and very easy to handle this question. So the second part in that question is assuming that the clay layer has a uniform thickness of 8.5 meter. So thickness is 8.5 meter. They want us to estimate its consolidation settlement. So it's very simple. So we know we have already proven in our previous videos that is delta, the settlement is equal to change in void ratio over 1 plus E naught into H, capital H, which is the total thickness of the clay layer. So here we can write, so 1.768 the initial void ratio minus 1.766 the final void ratio over 1 plus 1.768 into 8.5. So this should give you the settlement in meters. So if you multiply this by 1000 and change it to millimeters, it is around 6 mm. So this is the settlement of the clay layer due to the load increment of 50 kilopascal. Right? So this is the very first question which I have taken, and it's a simple question, right? We'll move on to the next question. Right, the second question is they have given us some data from a odometer test performed in a laboratory for a soil sample obtained from a certain location. The results from the odometer test are they have given the initial height sample of the height as 20 mm, the diameter of the sample has 50 mm, the initial void ratio is 2.93. The total settlement delta during the practical is 2.705 mm, and the compression index CC is equal to 1.329, and the recompression index CR, that is 0.396, and the pre-consolidation pressure sigma P dash is given as 200 kilopascal. So these are the details which are given to us from the laboratory practical. So in the field, the 16 meter thick layer subject to a 1.5 meter surcharge field. So they have obtained this from a 16 meter clay layer. So the clay layer is 16 meter and the fill is 1.5 meter. So this is the fill and this would be the clay layer. So they have taken this at a depth of 8 meters. So exactly at the center they have taken the sample. So this is 8 meters. From the top of the layer to the center of the sample, it is 8 meters. So compute the effective overburden stress. So they want us to calculate the overburden stress of the sample at the site. So the overburden stress is simply straightforward. So they have given a figure for us. In the figure, the water table is at the top of the clay layer. So the effective overburden stress sigma dash can be easily calculated. That would be so we need the saturated unit weights. So the saturated unit weight from the fill is 18.5. It is given in the figure. I will attach the questions to you in a document. I leave a link. Here the gamma saturated is given as 19.2 kilonewton per meter. So we can easily calculate the effective stress now. So it would be 18.5 into 1.5 plus 19.2 minus 9.81. This is due to the water into the depth 8. So this would give us a result of 102.87 kilopascal. So the next question is whether the soil is in normally consolidated state or over consolidated state. So you can see the pre-consolidation pressure is 200 kilopascal and the effective load in the current situation is 102, which is less than 200. So the soil is obviously in OC state, over consolidated state. So estimate the expected total settlement of the clay layer. The next question is, they want us to estimate the total settlement of the clay layer. As we did in the earlier question also, the settlement delta is equal to delta E over 1 plus E naught into H. In the meantime, we can write CR, the recompression index, is equal to delta E over log sigma 1 dash over sigma 2 dash. So combining these two equations, we can get delta equal to CR over 1 plus E naught into H into log sigma 1 over sigma 1 dash over sigma 2 dash. So here we can calculate, we know the value of CR, it is given us from the laboratory data 0.369 over 1 plus initial void ratio is 2.93 into the total clay layer thickness is 16 meter into log sigma 1 dash over sigma 2 dash. So here what would be the initial stress before the fill? So before the fill, the stress would be only this portion. So you have to calculate that part. So which is if you calculate it, it's a simple calculation. You will get it as 75.12 and the total load is 102.87. So solving this, we can get delta in millimeters. It is approximately 220 millimeters. So very simple question. Just you need to understand the concepts at which point, which compression index, whether the CR should be used, whether CC should be used. These are the things we have to keep in mind. So here in this question, since it is in over consolidated state, we know from the graph the CR portion, that is the recompression portion, should be used, and the respective gradient for that is the CR. So moving on to the next question. Here it is a bit different one. Now here you have to note in this question we have to note a major thing, that is the fill here. The fill we are using here is comparatively very large. It's infinitely large compared to the sample we are considering. So the load from the fill will be exactly same when we are moving along the depth. But in the case of the next question, where we are using a finite load like a raft foundation or a pad footing, where it is a small load, there would be a soil load dispersion which we have to take into the account. So in the next question, they have said us there is a 10 by 10 meter square footing foundation, raft foundation constructed on a clay layer. There is a net increase in contact pressure of 150 kilopascal due to the contraction of the raft at a depth of 2 meter. So compute the vertical effective stress at the depth of 5 meter from the ground level before construction of the foundation. So they are asking us to compute the effective stress before the construction. So they have given us a diagram. So this is the ground level. Here we have the footing. The footing exerts an even pressure of 150 kilopascal. The size of the footing is 10 by 10 meter squared. The water table is at this level. So this is 2 meter, and the clay layer extends up to here. So beneath this, it's an incompressible portion. So here it's 6 meter, and the data are given for us as gamma dry is 19 kilonewtons per meter cube, gamma saturated is 20 kilonewton per meter cubes. CR is given for us. CR is 0.05. CC is given for us as 0.15, and E naught is given as 0.8, and sigma C is given as 80 kilopascal. So these are the data given for us, and they are asking to calculate the load before the construction of the raft foundation. So sorry, the effective stress at 3 meter depth from the clay layer, or 5 meter depth from the ground level, which is the center of the clay layer. So we are considering a soil sample from this depth. So the load would be, it's very easy to calculate, sigma 1 dash. I'll take the sigma 1 dash. The sigma 1 dash would be before construction, right? So it is 19 into 2, because these here there is no water, so it's the dry unit weight, plus 20 minus 9.81 to reduce the effect of water into 3. So this would give us a value of 68.57 kilopascal. So the first part is done, simple as that. So the second part says as, compute the vertical stress increment at the same level due to the construction of the raft foundation, assuming there is a 1 to 2 load separation or load spread, sorry. So here they mean, so this is our foundation, which is 10 meter, and there's another 10 meter into the board, so square footing. So when we go 2 units down vertically, the spread is 1 unit in the horizontal direction. Similarly, either side there will be a spread. So here when we go by 2 units, there will be a 1 unit spread. So the stress would be dispersing in a somewhat in a triangular manner. So from the level of the footing, we are now down by 3 meters. We are considering a portion which is 3 meter at the depth. So here this is equal to, these 2 units becomes equal to 3, so that this would be 1.5 meter. Similarly, here this is 3 meter, and this would become 1.5 meter. So the total effective length would be now 13 meter, as this is 10 meter. At exact beneath of this footing, the load would be, so I'll take it as the increment delta sigma dash. So at the exact beneath, at the very bottom of the footing, so we can calculate the area as 10 square. So this would be the load applied by the footing. So this load would disperse in this manner, and at this depth, at this 3 meter depth, the area of the footing would be 13 squared, since it is a square footing. Similar dispersion will happen into the board also. Into the board in the sense, now if you consider this as the length, so this would happen in the breadth direction also, in the width direction also. So there also the length would be 13, so the area would be 13 squared. So this would give us an answer of 88.76 kilopascal. So this is the load increment. So easy, you have to remember when it is a finite load, so there would be a load spread. So you have to consider the variation of the area and calculate the load calculate the stress at the certain depth. Okay, in the third part, they want us to find the settlement happening due to this load. So if we see, before loading, before the loading, the effective stress on the sample, that is on the midpoint, is at 3 meter depth. It is 68, which is less than the pre-consolidation pressure. And after the loading, there's an increment of 88. So the addition would be somewhat closer to 150, which is higher than the pre-consolidation pressure. The soil is now getting transferred from the OC state to the NC state. So both the CR index and the CC index, that is the recompression index and the compression index, will get into the picture. So in the previous question we saw that delta, the settlement, can be written as CR over 1 plus E naught into capital H into log sigma 1 dash over sigma 2 dash. So here we are going to make a small change from the Schmertmann's graph, for the idealized graph. So this bend would happen at sigma P dash, that is the pre-consolidation pressure. So this would be the CR portion and this would be the CC gradient involving portion. So here the sigma 1 load, that is the initial load, would be the left of the sigma P, sigma 1 dash, and here this would be in sigma 2 dash. So this CR can be used only up to this sigma P until this changing point. After that the gradient changes, so CC. So we have to end this when the load is at the pre-consolidation pressure. So we know pre-consolidation pressure is higher than the sigma 1 dash, so it usually comes in the top, and here it's in the bottom. So this is a simple way to remember this. This is not the concept. This just you have to calculate the gradient, the difference of y-axis over the difference of x-axis. So from that this gets developed, but I am giving an easy way to remember. Just put the higher value on the top. So plus, we have to write this for this portion also, plus CC over 1 plus E naught into H into log. So here definitely sigma 2 will be higher, sigma 2 dash over sigma P dash. Again, this comes from the equation of the gradient, that is difference of y-axis over difference of x-axis, but I am using an easy way to remember this. So this is not the theory, this is just an easy way to keep it in mind. So just we have to substitute here. So this is CR is 0.05 over 1 plus 0.8 into H is 6 meter, into log sigma P is 80, the initial load is 68.57, so plus 0.15 cc, 1 plus 0.8 into 6 into log. So you have to take the sum of these twos. So this is only the load increment, not the final load. So we have to take the sum of these two. So the sum of those two values gives us 157.33 over 80, the pre-consolidation pressure. So when you solve this and convert into millimeters, it is approximately 158 millimeters. So here you have to keep in mind the clay is getting transferred from over-consolidated state to here in this portion it is in over-consolidated state, and here this is in normally consolidated state. It changes from OC to NC since it is passing through the pre-consolidation pressure. So the CR, CC both get involved. So there is a variation in the log portion, which is the load experienced by the sample. So it's just a small variation, and you have to consider here this is a finite load, so there would be a load spread, not a stress spread. There will be a load spread. So the spreading ratio is given to us as 1:2, that is two parts dropping through the verticals gives a spread in one part in the horizontal direction. So we can easily calculate the stress increment also. So not a hard question, just a small tricky part involved in that. So moving on to the next question, the last question for this particular Q&A. This is a question taken from Geotechnics of level 6, and it's an easy question to handle. if we understand the concept. So let's see. At a site, 12-meter thick layer of normally consolidated clay. So they have stated that at a site there is a 12-meter thick layer of clay. So there is a layer of clay. So this is 12-meter clay. Below a 5-meter thick of dense sand exists below. So there's a sand layer on the top which is 5 meter. So this is dense sand. A 5-meter high fill is constructed on the site over a very large area. So they are saying that there's a very large fill. It's a fill which is 5 meter. So this is an infinite load. And the water table is at top of the clay layer. So at the top of the clay layer we have the water table. The unit weights are given. For clay it's 16. So gamma for clay is 16 kilonewton per meter cubes. And for sand, so it is 20. For here gamma is given as 20 kilonewtons per meter cube. And for the fill it is given as 18 kilonewtons per meter cube. There is a table given for us for the variation of the void ratio with effective stress. So the sigma dash values are 50, 100, 200, 400 and 800 in kilopascals, and the void ratios are 1.82, so 1.77, 1.68, 1.56 and 1.3. So they have asked us to subdivide the clay layer into 4 sublayers of equal thickness and compute the effective vertical stress at the center of each sublayer before and after construction of the fill. So they want us to divide this clay layer into 4 sub portions. So when you divide into 4 sub portions, so this is the first portion, so 2 portions and 3 and 4. So each portion has a thickness of 3 meter, and they are asking us to compute the load at the center of each portions before and after applying the fill. So I'll just show it for one part. It's very easy. So before construction, at A, the load sigma 1 dash would be equal to, so before construction, so there is no fill, so only the sand and the clay layer. So from the sand we will get a load of 5 into 20 plus after from the clay layer it would be, the depth would be only 3 by 2, 1.5 meter, because at the center, so 3 by 2 into unit weight 16 minus 9.81 to reduce the effect of water. So each layer is 3 meter. So we can find out the final answer. So the final answer is somewhat around 109.3. So this is around 109.3 kilopascal. So what happens after filling it? So once you fill it, you are just adding 5 times of 18 of stress. So you are adding 90 kilopascals. So after load, so you'll get sigma, let's say sigma 1 dash A after 109.3 plus 90. Simple as that, 199.3 kilopascal. So each layer, what would be the changing part? If you want to calculate it for B, you have to just change only this depth. So it would be 4.5. So 3 from this and another 1.5. So here it will change it as 4.5, that is 9.9 by 2. So you will get the answer and add 90 for that, because that is the increment for everything. So it won't change because this field is infinitely large. They have said it is infinitely large. For each load, then you can calculate what is the load before. So each point, so you can calculate what is the stress before loading, before this fill, and after that fill. So I have done the calculations already. So I'll just write it down. And the next part is determine the consolidation settlement of the clay layer. Now there is another picture, right? So in the meanwhile, I am writing the answers. I'll just explain that. So here they have asked us to calculate the settlement of the entire layer. So we know when we use the equations, we know we need the void ratios for each stress. So how to calculate those void ratios? So this is before and after, I mean the loading, before loading and after loading. These are the points A, B, C and D. So before loading, as I calculated earlier, this is 109 in kilopascals. So the increment would be 90, so 199.3. So that is for A. And for B, the answer is around 127.9. So here it is 217.9. Just add 90. For C, it's 146.4. So here it is 236.4. Here for point B, it's 165. So here it's 255. So simple. So how to find the void ratio? So these details are given to you. So here, this is a bit graphical part. You have to do it individually. Take a graph sheet, draw it to the scale, in log scale or in arithmetic scale, whatever it is. But use the proper scales and draw the graph. And from the graph, you can find all these pressures in the x-axis. And from the y-axis, you can find all the void ratios, respective void ratios. I have done that, and I'll write down the void ratios also. So the void ratio before loading, here it's 1.76. So after loading, it's 1.68. So in red pen, I have written the void ratios. In red ink, it's a void ratios. For B, it's 1.74. For C, it's 1.72. And for D, it's 1.71. Similarly here, for B, it's 1.67. And for C, it's 1.65. And for D, it's 1.64. So the thing you have to do, take a graph sheet, draw it to the scale, draw the graph, mark these stresses in the x-axis and find the respective void ratio. Simple as that. Very easy. So now you know what are the void ratios. So you have to only find the settlement. So again, I will do it for one portion for the A point, that is the first layer. So we know delta is equal to delta E over 1 plus E naught into H. Right? We know this. We have proven this. So change in void ratio, that is 1.76 to 1.68. The change is 0.08 over 1 plus 1.76 into thickness of the layer is 3 meters only for this layer. So it is 3 meters. So the answer would be 0.087 meter. So this is only for the first layer. So similarly, you can calculate it for the second layer, third layer and fourth layer. And if you add up all this, you will get the final settlement of the total clay layer. So this is a practice which we have using in the upper levels, that is the students who are following geotechnics, we do this to find the accurate settlement of the clay layer. If you consider this as an entire single layer, the settlement would be different, and if you considering it in separate layers, the settlement, we can get the accurate value of the settlement. I think you would have understood and gain some knowledge from this Q&A session. If you have any queries, comment down and like and share the video and subscribe to my channel. See you soon in the next video of the further continuation of consolidation.